Thank you to the organizers for having me and organizing a good first day of talks. So yeah, today I'd like to talk to you about flagged LLT polynomials and time permitting their application. And this is all sort of joint work with, I guess now a long-time group of collaborators, Jonah Blasiak, Mark Haiman, Jennifer Morse, and Anna Kuhn. So yeah, let's get started. So first, I'll give the talk, or in the talk, I'll talk about sort of some key objects that are hopefully friends of many of you, but if not, I'll show you my friends and they can be your friends too. All right, so I like working with symmetric polynomials, right? And by this, I just mean, polynomials where if I permute to the input variable, they get the same output polynomial. And it turns out that if you take the ring of such things, then you can write them in terms of these generators, these elementary symmetric polynomials. Instead of walking you through the definition, here's some examples of them. And if you've never seen them before, I think you can kind of get the idea. You just sum up all the square-free monomials, and then this has to be symmetric, right? Because you did it in all possible ways. Okay. And in some sense, it's sort of immaterial how many variables you're working with. You can just sort of take larger and larger numbers. And since any symmetric polynomial, it turns out, can be written as a polynomial in terms of these elementary symmetric polynomials, we often will just write any symmetric polynomial in terms of these generators, these elementary symmetric polynomials. And in this way, I'll often call them symmetric functions, even though they're not really functions. That's just a historical term. Okay, so we have these things, and but of course they actually form also a vector space. So if I restrict to degree d, right, then if I add to symmetric functions, they're still symmetric. And so this is a vector space, and of what dimension? Well, it's integer partitions of d. So I think many people have seen integer partitions before, but if not, so an integer partition, right, is just if I fix an integer partition of it is a weakly decreasing sequence of integers that add up to it, positive. And so here I've written out all of the partitions of 5. And as combinatorialists, we often like to take structures and draw pictures out of them. And so in this way, I'm going to represent partitions instead via what's sometimes called Young diagrams, or based on Pairs diagrams. Now, many of you probably don't notice something that's a little different from what you're used to. So throughout this talk, I'm going to use French notation. I'm sorry if you're familiar with English notation, and if you don't know what I'm talking about, don't worry, I'm right, and they're wrong. But the way this works is, so for instance, like 3, 2 is a integer partition of 5, right? And I'm just going to put 3 boxes on the first row, 2 boxes on the second row, right? And then that illustrates my integer partition. Okay. So as I said, we like to draw pictures. One reason that maybe this will seem unmotivated if you've never seen it before, but I like this is because then we can take these boxes and we can fill them with numbers according to a certain rule, and ask, well, okay, like how many of these things are there and whatever. So these things, what I'm going to do is I'm going to say I want to fill the boxes with numbers such that it strictly increases as I go up the columns and weakly increases along the rows. So for instance, if I take the partition 2, 1, that's the partition of 3, and I fill it with the numbers 1 through 3, then these are my 8 possible semi-standard Young tableaux. Okay. And these have a tendency to show up in various places in combinatorics, so we like them a lot. Now, what I like to do with them is construct symmetric polynomials. So I want to associate a symmetric polynomial to these combinatorial objects. So what I'm going to do is I'm going to list them all out, and then I'm going to replace all of those numbers with variables. So like 1 becomes x1, 2 becomes x2, and so on. And then to each one of these fillings, right, I'm just going to take a product of their entries and add them all up. Okay. So I get this polynomial with 8 monomial terms, except this one, of course, shows up twice, so it becomes both 2. And this ends up being a symmetric polynomial, which you can check manually. It's not obvious from this construction that it should be, but it's not so hard to work out some combinatorics to show it. So this recipe in general gives us maybe my favorite symmetric polynomial, which is called a Schur polynomial or a Schur function. So you just fix your partition, you sum up over, you look at all the ways to fill the partition diagram with numbers. This gives you semi-standard Young tableau, and then you just repeat this process and you get out a polynomial. Okay. Any questions about Schur polynomials? So yeah, it ends up actually being symmetric. Like I said, that's not obvious, but it's not so, it's an exercise. And they also form a basis for our symmetric function ring. So we write any symmetric function can be written in a unique way as a unique linear combination of Schur functions. Okay, so why do we care about these things? Well, one reason is this is a fact from representation theory, but irreducible representations of the symmetric group are also labeled by partitions of n. And so, for instance, if you want representations of S3, here's the three irreducibles. This is over field characteristic 0, like C. And people cooked up a map, the Frobenius characteristic, that associated to each representation of Sn a corresponding symmetric function. Okay, and I'm not going to give you a definition of it, how to compute it, but there's a formula from the character table. But it has the following properties, and this is what actually matters. So the first one is that if you hand me an irreducible Sn representation indexed by a partition, remember the indexed by partitions, then its Frobenius characteristic is the Schur function. But more than that, it is structure preserving in some sense, or like it encodes the structure. So if I have a representation that is a direct sum of two, then under the Frobenius characteristic map, it becomes a sum of symmetric functions. And then there's also a product structure. So if you do an induction of symmetric group representations in sort of a straightforward way, this gets mapped to a product of symmetric functions. So just like one example is if you took like this trivial representation of S1 cross S1 cross S1 and induced it up to an S3 representation, then under the Frobenius characteristic, this just gets sent to the Schur function indexed by the partition 1 cubed, which then just using basic linear algebra, you can work out as it expands how it expands in terms of Schur polynomials. And then these coefficients are telling you how many times each corresponding S3 irreducible representation is occurring in this representation. Okay. So it's a nice computational tool. And it sort of underlies a hidden guide that I think a lot of people who work in sort of my area of symmetric function theory use but don't always say, which is, and the reason I don't say this is a little imprecise, but I'm cluing you in anyway. So if you come across a naturally occurring symmetric function, you're doing whatever you do, and you come across a symmetric function, and then you expand it into the Schur basis, and all of the coefficients are non-negative, then this means there's potentially, probably, some sort of representation theoretic thing going on behind the scenes. And that you can't just know what it is, but like maybe you can work it out, but that's like a guiding question in general. So people, whenever they come up with symmetric functions, if it ends up being computationally Schur positive, that's surprising, and they want to chase that. Okay, so that's one of the things I like to do. Okay, so yeah, this was mentioned in the morning, but so Schur polynomials, if you take their products, right, we sort of already said that could be interesting theoretically, but it's also interesting representation theoretically. So if you want to take a product of two Schur polynomials, expand it into Schurs, there are these coefficients, they're called Littlewood-Richardson coefficients. And for representation theoretic reasons, right, these all have to be non-negative integers. And there's lots of combinatorial formulas for them. So yeah, it's like a very beautiful enriched area. But one other thing you can sort of use with them is you can define something called a skew Schur function, where you take some partition shape, and I'll give you an example. Maybe let's just do it here. Like here, take 32, and then you cut out a smaller partition from below. And you can define this as using Littlewood-Richardson coefficients, or more straightforwardly, you can give its monomial expansion by actually just the same recipe as with the Schur function. You just draw this diagram and fill it with the semi-standard Young tableau rules and associate monomials and add it up. Now, what if we want to be a little more basic? So instead of doing a Schur expansion of these things, what if we just wanted a monomial expansion? Well, sort of straightforwardly, I'd say, well, I know monomial expansion for each of them. Monomials multiply in like the easiest way forward, possible, right? You just multiply them together and then add up the exponent vectors, right? And you can get a nice monomial expansion of this. So, for instance, if I want a product of these two Schur functions as a monomial, I just have to go over all pairs of semi-standard Young tableau. Okay. And this is relatively straightforward to do, but I just want to point this out because that's going to motivate where we're headed next. So are there any questions about skew Schur functions or what's going on here? Okay. So we have this nice combinatorics. Now, one thing that people like to do is they like to take these symmetric function things and they like to do something called q-deforming them. So without maybe totally motivating it, but coming from various perspectives in sort of the mid-20th century, people started wanting to introduce q parameters into the coefficients in various ways, and and push this program forward. And so I want to present to you actually something that is a q deformation of a product Schur polynomials. And this is what LLT polynomials are. So let me tell you about LLT polynomials. So an LLT polynomial, it's going to be a symmetric function, and it's going to have coefficients that have this extra parameter q floating around. Okay. And they're going to be indexed by an arbitrary tuple of skew shapes. So like here, I put a tuple of skew shapes. This is 3, 2, skew 1, and then 3, 3, skew 1, 1. Okay. And then what I'm going to do is I'm going to align them according to their content diagonals. So for every box, you can compute its content. That's just the difference between its column number and row number. Okay. So here I've taken these two shapes. I've put them in a plane so that there's 0 content diagonals line up, their 1 content diagonals line up, and so on. And then I'm going to put a reading order on them. And the way this is going to work is I'm going to go diagonal by diagonal in order of increasing content and read from the bottom left to the top right. So on this, if I read here, I hit B1 first, go up, then I come back down to the next content diagonal, B2, B3, come back around, 4, 5, 6, 7, 8. Okay. And then I want to define a notion of attacking pairs. This is the definition, but maybe I'll just say it out loud because it's almost easier that way. Is that if two boxes are on the same content diagonal, we'll say that they're attacking. But also if I have a box and then I have another box in the next content diagonal below it, that will also be attacking. So let's do these. So for instance, B2 and B3, they're in the same content diagonal, so they're attacking. But B3, as I'm reading, I come back around and I hit B4 before I've returned to the shape of B3. So this also forms an attacking pair. Okay. And then B4, B5, and B4, B6, they're attacking by they're on the same content diagonals. And then B5 and B7, because this is one more over and I haven't returned. And then same with B6 and B7, and then finally B7 and B8 are attacking.
So sorry, are B5 and B6 attacking?
No, yeah, if they're in the same shape, they don't attack. Yeah, sorry. Only across shapes can they attack.
Does it not matter how can you translate the shape along the diagonal?
Right, yeah, you could translate as much as you want. Yeah, that doesn't matter. It's just about the reading order. Yeah, good question. Of course, you can also translate the whole configuration. left, right, or whatever. Yeah. The important thing is just that the diagonals are aligned correctly. Okay, bear with me on that. So, okay. So I said I wanted to define something that's like a q-deformation of a product of Schur. Right now, this is missing a bunch of stuff because if I didn't want to add in a q, if I just wanted a product of Schur functions like the ones I gave before, right, all I would do, I wouldn't care about this whole reading order thing I just said. I'd just have the shapes, I'd fill them with all possible ways. That's semi-standard Young fillings. And I would sum up over those monomials and I'd have the result. But we want to associate an extra q parameter to each configuration. And the way we're going to do this is we're going to define something called an attacking inversion. So the way this is going to work is we're going to go back and looking at these attacking pairs, and anytime they form an inversion where there's a decrease, right, then that will contribute a q factor. So let's do this example. So for instance, as I'm reading, remember these two boxes formed an attacking pair, but 4 and 5 increase, so it's not an inversion. But then when I look at these boxes, remember these two are attacking, but 5 decreases to 3, so that's an inversion. Okay. Similarly, 3 these two boxes are attacking, but it decreases, so that's an inversion, non-inversion, non-inversion, inversion, inversion. So there are 4 inversions in this picture, and so this will contribute a q to the 4th times the x monomial that we would have expected from before. Okay, and this is how we define our LLT polynomials. Okay, so from a combinatorial perspective. Now, there are a few things that you should complain about. The first is it's no longer at all obvious that that's a symmetric function, because these q parameters might. I said before I had some argument about the Schurs being symmetric, but I didn't. Now I introduced this q. The things that I were saying makes a symmetry. Now you have to make sure the q things line up, but they do. It's not too hard to show once again. If we forgot about the q, right, then it is just a product, right, of Schur polynomials. So why are they called LLT polynomials? That's after Lescu, Leclerc, and Thibon. They were exploring some representation theory, box-based stuff with UQSLR hat. I'm not going to talk about that, but just for history. And sort of importantly, or if you want some sort of connections about many things that people in the room are a little more familiar with, if your indexing shapes are non-skew, then the LLT polynomial, when you expand it into the Schur basis, remember that's a basis, you can expand it, those coefficients are essentially parabolic Cauchy-boosted polynomials. Okay, but more importantly, for any tuple with skew shapes, if I expand them in terms of Schur polynomial, those coefficients are positive, and by positive now I mean that the coefficients are in like n, right? So if each coefficient is a polynomial in Q, and that one has non-negative, each polynomial that's occurring as a coefficient has non-negative integer coefficients. Okay. So if I can write something in terms of LLT polynomials, then I know it's Schur positive. Okay. So I have this thing with some nice combinatorics monomially, but then if I can just group whatever monomials I have into LLTs, then I automatically get a Schur positivity result for free, or using the work of Bernousski. Okay. And so this really motivates, I think, why, at least in algebraic combinatorics, from my perspective, LLT polynomials show up a lot, is because they're a nice way to take something combinatorial and establish Schur positivity. Okay. I will mention, right, of course, one problem with that approach is that now, because they're indexed by a tuple of skew shapes, there's too many of them to form a basis. So if you hand me a symmetric polynomial and say write it in terms of LLTs, there's no longer a unique expansion. So you can't just put it into a computer and hope it'll fall out. You have to do some work there. Okay. But I want to give you some examples of where these things show up. So, and it's okay if you don't know what these things are. This is just to kind of give you vibes. But the first thing is the Haglund, Haiman, Loehr formula for Macdonald polynomials. So I'm not going to define a Macdonald polynomial, at least not yet, but there are some symmetric functions with coefficients in q and t that Haglund, Haiman, and Loehr were able to write them as a sum of LLTs indexed by skew shapes that were ribbons, so they had no 2x2 boxes in them. There's also something called the shuffle theorem, and a lot of its generalizations. This has been a big business in a certain corner of algebraic combinatorics, where you had some sort of algebraic thing coming from some representation theory, and you wrote it combinatorially in terms of LLT polynomials. So that's like another sort of notable instance. And then a third sort of application is people have been talking for the last few years about, or the last many years about chromatic symmetric functions. These are a certain kind of symmetric function you can associate with a graph. And in particular, if you have an incomparability graph for a natural unit interval order, then there's some q or t deformation of this. And it turns out that this is essentially something called a signed LLT polynomial, which we'll talk about later. Okay. So these are just like some examples of LLTs showing up.
Is there a representation theoretic interpretation of LLT polynomials?
So yeah, the way that they are shown to be Schur positive is using some pretty hardcore Cauchy-Lucid theory. But in terms of like, is there some representation that they're a character of? No one knows. Yeah, like that's an open question. That would be really cool.
Well, will it exist as a direct sum, but not?
Sure, yeah, like a natural, a nice way. Yeah.
Well, the unicellular ones, there is an answer to that question. But
Yeah.
special cases, yes.
Certain special cases, yeah. Okay. Any other questions about LLT polynomials?
So it doesn't depend on the ordering of the skew shapes?
It could depend, right? If you had a bunch of them and you swap their order, that could mess up that inversion combinatorics. But there is a rotation theorem, so you can take your shape at like one end and rotate it around, right? Because everything's about the diagonals. Yeah. And then of course a q equals 1 in degenerates. Yeah. Okay. Great. So that's LLT polynomials, everything I want to say for now. Now I want to move into, and we've seen a little sampling of some things like this, but a way to create certain polynomials that are no longer symmetric, but reminiscent of symmetric polynomials. So now I want to fix a partition, but I also want to fix a flag. And all I mean by a flag is just a weakly increasing sequence of non-negative integers. Okay. So then I want to define a flagged semi-standard tableau with an associated flag B. And all this is I have my shape lambda, and then I'm going to fill it with numbers as before, but I'm going to have an extra rule where if I pick the flag, I'm going to bound row I by the number bi. So in this example, I have shape q1, and I fix the flag 1, 3. And so what I'm going to do here is I'm going to say I want to take all semi-standard Young tableau where the first row is bounded by 1 and the second row is bounded by 3. Okay, so now if I take the collection of all such things, there's only 2 of them. So it significantly cuts down, typically, if you bound things, the number of semi-standard Young tableau. And then, okay, you can play the same game, right? You can associate a polynomial by just each tableau is giving you a monomial, and you just add all up. And you get a nice thing called a flag Schur function, or flag Schur polynomial. And these were studied, well, they first appear in Lascaux and Berger's paper on Schubert polynomials. At the very end, they just kind of mentioned they exist. And then Michel Wax, took a lot of that and developed the more combinatorial theory associated with them. For those who are sort of more versed in the symmetric function theory world, I'll just mention there is an associated sort of Jacobi-Trudy-like formula. If this doesn't mean anything to you, don't worry about it. But as an example, right, like from our example before, if we have our shape 2, 1, flag 1, 3, then this is our flag Schur polynomial, right? It's just the sum of those two binomials. Okay. And so why were Lascaux and Berger interested in them? Well, flag Schur polynomials are actually examples of special Schubert polynomials, which came up in Colleen's talk. And specifically, they correspond to 2, 1, 4, 3 avoiding permutations. And this sometimes goes by the name of vexillary, but that's not really informative because vexillary just means flagged. And also, interestingly, due to Reiner and Trezzono, these are examples of another family of sort of symmetric function inspired like polynomials called de Mazur characters. So let me explain what de Mazur characters are. So you can define something called the de Mazur operator that acts on any Laurent polynomial, like so. And then the de Mazur characters, or also they're sometimes called key polynomials in type A, are constructed as follows. So if my de Mazur character is indexed by a partition, then it's just this monomial, right? Indexed by the partition weight. And then if it's indexed by anything else that's not a partition, it's not a decreasing sequence of integers, then I can iteratively construct it by applying these de Mazur operators. So let's do an example. Right, so for instance, if I have D520, right, that's just x1 to the 5, x2 to the 2, x3 to the 0. But then if I have 250, right, like that was given by swapping positions 1 and 2. And so that I got that by applying pi1 to D520. And right, if you compute that out using that explicit formula, you get this sort of like root string like expansion of monomials. And then you can just keep iterating, right? So if I had 205, well, that just differs from 250 by swapping that 5 and 0. So it's just pi2 applied to this result. Okay. And you can keep doing that over and over again. Okay. And they're called characters because they really are characters of something called irreducible B modules, where in this instance, B is our like group of upper triangular improvable matrices. So these show up, right? And like I said before, the flagged Schur polynomials are a special case. And then sort of bear with me, I want to introduce one more family of non-symmetric polynomials that is closely related to these de Mazur characters. And these are called de Mazur atoms. So they're the same as the keys or the de Mazur characters, except you replace everywhere you had a pi I with a pi I hat. Okay, so they have a little hat. And that's just pi I minus 1. So you say, once again, it's indexed by a partition, it's just a monomial as such, and then you can compute it iteratively by applying the pi I hats. Okay. And instead of like writing all that out because it gets kind of messy, it's actually kind of more insightful to think about it the other way around. So de Mazur atoms are related to de Mazur characters by sort of a Bruhat order inclusion-exclusion type formula. So in particular, every de Mazur character is a positive sum de Mazur atoms. And sort of maybe importantly for motivation, the reason I want to mention them is just that they are sort of a dual basis for the de Mazur characters under sort of a nice inner product that's sort of motivated by the representation. So let's, I see, okay, yeah, one more thing. So why did I bring all these up? Well, the point is that all of these things are related to symmetric functions, but like how are they related? Okay, so maybe the easiest thing to relate back to a symmetric function is, of course, if I take my flag Schur function and I just make my flag really big and constant, like n, then of course I would just get the Schur polynomial by combinatorics, right? I just didn't bound anything. But a sort of more non-trivial way to relate things is by applying a certain sequence of de Mazur operators. So for any reduced word in the symmetric group, I can construct a pi sub w, which is just an iterated, a product of these de Mazur operators associated to that reduced word. And you can show that this is well defined. And then I want to define, so if I take w naught, which is the longest permutation in Sn, then pi sub w naught is special, and we'll call it the Weil symmetrization operator. And you can show that whenever you apply this operator to any multivariate polynomial, the result will be symmetric. And when I apply it to my flag Schur polynomial, I get a Schur polynomial. When I apply it to my Demeter character, I also get a Schur polynomial. And if I apply it to my Demeter atom, I either get a Schur polynomial or else I get 0. So I get one or the other. So all of these things serve as some kind of generalization of a Schur polynomial into the world of non-symmetric polynomials, or just polynomials. So here's just like a summary picture for you, right? So I have these three generalizations. They all file symmetrize to Schurs, except sometimes this atoms become 0. And the Demeter characters are positive sum of the atoms, and the flag Schur polynomials are a special case of the Demeter characters. Any questions about any of that? Okay. So then, right, we spent this time talking about Schur polynomials, and we talked about their generalizations. We talked about LLT polynomials as some sort of like q-deformation of a product of Schur polynomials. So then a sort of natural question that I just don't think anyone really thought to answer is that you could ask, well, is there some sort of nice family of polynomials that is non-symmetric sitting above like the LLT polynomials in this picture, right? So it's something that Weil symmetrizes to an LLT polynomial. Now, of course, once again, what's nice mean? Okay. I'm going to pose that nice means something like Schur positivity. So maybe something that's positive in terms of one of these things in the top row. Okay. So let me tell you then our proposed solution to this problem. So what we're going to do, going back to our LLT polynomial, is we need to figure out how to flag that combinatorics, how to put bounds in a sensible way. So what we're going to do is we're going to go look at the row ends of the various shapes in our tuple of skew shapes, ordered in reverse reach order. So remember before, we were reading diagonal by diagonal, starting from the bottom left to the bottom right and sort of sweeping this way. So let's reverse that process. So that means we hit this end first, then this end, then this one, and eventually this one, right? So those are my 4 row ends in reading order. And then my set of flagged semi-standard tableaux on this object is just going to be the same rule. So if I fix a flag, right, like 1, 2, 3, 4, then, right, I just bound the various rows in that order. So my flag was 1, 2, 3, 4, but now I have to bound this row first, then this one, then this one, and then this one. And so I've written those bounds there. And then I just fill it in semi-standard Young tableau in the same way and compute the inversion statistics the same way and get out a polynomial. And it's not symmetric. Okay, let's do a small example because that one's too big to carry it out and really see what's going on. But for instance, if my tuple of shapes was just these 2 dominoes and my flag is 1, 2, then I get these 3 tableaux, and the red arrows indicate where I have my attacking inversions, right? And then I got to change my variable q to t. It's just a parameter, right? And so I get the sum of these 3 binomials. Okay. That's how you compute this. Yes.
Is there a reason why you need the b's to be increasing?
Right. So the definition makes sense without it, but to get the nice properties we need to do this. So like combinatorially, yeah, you could just define any bounds on any rows, right? But this turns out to be sensible for, what am I going to say next? The various properties that we want. Does that make sense? Yeah.
Yeah. I mean, how did you find that this was the correct order of the b's?
A lot of computation. Yeah, it's not so obvious, right? Like why you should do this. And I don't know if there's some structural reasons that I guess we could give now, but but this is basically why. So I mean, first is just that this result actually does Weil symmetrize to your usual LLT polynomial. The second is when you follow this rule, of course, with a single shape, this is the same as bounding your single shape by going like up, you know, like it wouldn't make sense to bound your like second row by a number smaller than your first row, right? Because then you effectively just bounded the first row as well. Okay. The other one is that we were able to, and I'm not going to write it out because it's a little messy without more work, but we could actually also give an algebraic formula using a tool called nonsymmetric called Littlewood polynomials. So we were able to connect a combinatorial formula to a more of just like a certain algebraic formula. But maybe sort of most importantly, conjecturally, these things expand positively in terms of denser atoms. Okay, so right when I expand their coefficients in terms of denser atoms, they're all polynomials with non-negative integer coefficients. Okay, and why this is nice is because this means there could be potentially, hopefully, someone maybe needs to find it, a representation theoretic meaning for these things. Okay. Great. Okay, so are there any other questions about these objects before I move forward? Yeah.
Oh, sorry, I think you mentioned earlier about Q because one specializes to the like usual, but is there anything interesting that we can say about Q equals 0?
Yeah, that actually is like, because that's like inversion list fillings. Yeah, that is like an interesting topic. I guess I haven't thought hard about what you get exactly in this flagged case, but yeah, certainly for like LLTs, that it comes up. Yeah. Yes.
Is there Schur positive like thing for like LLT polynomial?
Yeah, that's what this conjecture is. Yes, exactly. So this is our analogy to Schur positivity, is that, I mean, it's a conjecture, we can't prove it yet, but that in fact, this is sort of the right idea for that generalization. Yeah. So maybe, yeah, then I sort of mentioned in passing, there's a variation on these things called signed flag LLT polynomials. And I think even if you sort of have not loved what I've said so far, this is worth paying attention to because it's kind of just a nice trick in combinatorics and tableau stuff. So before we filled our tableau, right, with numbers like 1, 2, 3 up to n or whatever. But I want to define, you could really define it with other sort of numbers or letters or whatever you want, as long as you have like a total order. So I want to define a signed alphabet where I have 1 bar, 2 bar, and so on, ordered as so. And then I'm going to have these barred letters behave sort of differently than the unbarred letters. So the unbarred letters, the usual ones, will behave as before, weakly increasing along rows, strictly up columns. But the barred ones will do the opposite. They'll actually strictly increase along rows and weakly increase up columns. And then if I have my flag, right, I can still just pick bounds, and then because it's a total order, that makes sense. And so then I'm going to define something called a signed flag LLT polynomial, where I just go over all such fillings, but the binomial weight I associate to it will be will compute the inversions in the same way, but the barred letters will contribute a minus t inverse times xi. So we'll do an example. So for instance, going back to our 2 dominoes, if I want to fill it with a signed alphabet, where I've bounded this first row by 1 and the second row by 2, well, when I bound something by 1, that's the smallest letter, so these all just have to be 1, 1. But if the second row is bounded by 2, well then I can have a 1 bar, or a 2 filled in there. And I fill them in as before, but following these rules where the bars are sort of like behaving in a transposed way. And then I compute the associated monomial. So like for instance here, this is where like these two are the ones with the bars. So like here we had a single inversion that's contributing a t, but then this 1 bar contributes a negative t inverse. So that t and t inverse cancel out, and you just left with minus x1 to the 4th. And then similarly for this one, you get some cancellation. And so you get, and then potentially, even though you have this combinatorial formula, you can have internal cancellation. So like this whole thing actually just collapses to a monomial. That's a bit of a just a small example issue. So in general, Seinfeld flag LLTs are not typically positive in terms of atoms, and they're generally not even positive in terms of monomials. They'll have a lot of like minus terms floating around in their monomial expansions. Okay. So why did I bring these up at all? Like, why would you care? Well, so this gets to the heart of maybe like why we even started caring about the flag LLTs in the first place. And it's sort of the following thing. So we wanted to define a special map for reasons we'll get into in a second that took these signed flag LLTs and mapped them to flagged LLTs. Now, remember, there's too many LLTs to form a basis, right? Like you have many of them. So if I just took a map and I said I want to send each of these polynomials to another one as a linear map, that's overdetermined, right? So most of the time you just say there's no solution. But it turns out that if you actually tell the computer, like I want to take the signed flag LLTs and map them to the corresponding unsigned one with the same combinatorial indexing data, this actually is well defined. Okay. Generically, like you would never expect this kind of thing to work, but it actually works. Okay. And so why do we do this? Well, this is some sort of like non-symmetric analog of a map that showed up in the symmetric function theory a lot, associated with Macdonald polynomials and LLT polynomials. Okay. And so this is like, we think of it as like a map that sends signed combinatorics to unsigned combinatorics. So yeah, what are some sort of applications of this? So using this machinery, we were able to generalize the sort of like the Macdonald polynomials that I mentioned before. That remember they had a Haglund, Haiman, Loehr formula in terms of some sort of LLTs. We were able to replace that with flagged LLT polynomials and get some sort of special variation on a non-symmetric version of Macdonald polynomials that are distinct from typical non-symmetric Macdonald polynomials. So we're calling them modified R non-symmetric Macdonald polynomials, or modern Macdonald family polynomials for short. And these are, as a result of being a sum of flagged LLT polynomials, are conjecturally atom positive. We were also able to take this sort of like shuffle theorem from before, a non-symmetric shuffle theorem, and there was the shuffle theorem before with the LLT polynomials. We were able to replace that with flagged LLT polynomials and get a non-symmetric variation of this shuffle theorem. And then sort of finally, so Tawari, Wilson, and Zhang defined some sort of non-symmetric chromatic polynomial to some sort of dig path. And these are essentially examples of signed flagged LLT polynomials. So one sort of reason to mention these signed flagged LLT polynomials is because they're the right thing to connect with chromatic symmetric functions. Okay. Let's see. So then, yeah, we only have about 5 minutes left, and maybe I don't want to spend too much time on digging into what Macdonald polynomial is. So maybe I'll sort of jump ahead to the end. So sorry about this. We went a little slower, but I'm happy for that. So yeah, why do this? So in general, flagged LLT polynomials serve as some sort of combinatorial generalization, symmetric LLT polynomials and flagged Schur functions. So from a purely combinatorial perspective, I think they're quite interesting. But also, maybe sort of importantly, the flagged LLT polynomials and their sign variants provide some sort of new common framework for understanding these various questions coming from Macdonald polynomials that we didn't have really time to understand. And then finally, I think that they just generally provide a new way to enter into and understand the entire sort of diagonal harmonics and shuffle theorem program, which if you're not familiar with, that's okay. But this has been an ongoing body of research, and I think it sort of gives a new foothold into it in a more combinatorial way. So with that, I'd like to thank everyone for their time.
questions for George? Yes. You have these two linear maps, right? With the file centralization map.
Yeah,
And it won't be, it's not operator, it's spaces.
yeah.
Maybe you can still ask like rank the matrices. Perhaps I need to substitute values in QT.
Wait, so you want the rank of the flag plethysm matrix or the?
I guess you have two linear maps.
Yeah.
When you define the vowel symmetrization.
Yeah. So the flag plethysm is an invertible map. So that's easy. Vial symmetrization. I mean, you're sending something that in a fixed degree is have the basis of all I don't know, weak compositions of a fixed length that add up to D, and mapping it to a space with integer partitions, and it's like surjective. So yeah, you have to work out that combinatorics, I guess. Yeah.
So the tableau you define where like the barred and unbarred tableau, they appear in supersymmetric crystals.
Yes, yeah. So yeah, people call this like supersymmetric combinatorics and stuff.
Yeah, cool. So have you considered like the positivity in like some kind of like supersymmetric Demesure characters?
Yeah, I tried that a little bit, but yeah, I guess at least what I tried didn't work out. But I'm not an expert in that, so maybe I messed something
Is the pletheism from the signed flagged LLT polynomials to the, I mean, it's probably not, but it feels like, is it just set all the X bar variables to 0?
No.
And then you don't get those fillings and you get the usual
Well,
fillings?
like combinatorially, yes, but maybe it's like it's kind of surprising because this is a linear map, right? It's just a matrix. So like to define it as take a combinatorial thing and do this, that's like a surprising result. Right, or like
What
it's
about
a
the polynomials and then set these variables to
Oh,
that's obviously
but once you've computed the polynomials, you no longer have, you can't distinguish, like once you hand me the polynomial, which things came from a bar and which didn't, right? Like in the example I gave, they canceled out.
Oh, that's right. Okay,
Yeah.
Okay.
No, but yeah, thank you.
Just
Yeah.
Is there an algebraic pathway to prove these things are positive in terms of the Demesure atoms?
Okay, I think there is technically yes, but I think it's like there's a lot of work to do there. Like so these Demesure, so something to be Demesure atom positive means there's some sort of like filtration of D modules that's good, and like this is in a precise sense. But like I guess there isn't like a clear sense of like how I would try to cook up such a thing, like given just one of these polynomials, if that makes sense. So alternatively, it might, because these atoms are dual to these characters, there might be something about showing like you have a certain Hom space or something that corresponds. I think it's still pretty wide open, but there should be. If the world is just, the answer to your question is yes. No more questions. Let's thank George again.